When I came in the morning, I just realized the room name is Ramanujan. Can you guys hear me? Yeah? You said no? Oh, okay. You fine, right? Everyone fine? Only thing is these lights are really blanking my eyes, but I think I'll manage it. I think you need it for the camera. I remember when I was a kid, I liked mathematics, and I remember about Ramanujan. He made an interesting comment. Have you heard of the number 1729? The significance of the number 1729? Yeah, it's apparently the smallest number that can be represented by the sum of cubes of two different sets of numbers. That's the smallest number you can represent as the summation of the cubes of two numbers, 10 cubed and 9 cubed, and 12 cubed and plus 1 cubed. It's 1729. Anyway, I just remember that about Ramanujan. I know you guys were maybe in the keynote session. Just to make sure that you come out of that session and focus here. I would like to do a small exercise with you guys. Have you heard of yoga? You guys do yoga? Yeah. Well, the major component of yoga is actually breathing exercises. So let's do a little bit of just a simple breathing exercise. You can keep your eyes open or keep your eyes closed. Take a deep breathe inside and exhale after. Make sure the exhalation is longer than inhalation. Go ahead, please. Join me. Okay. How long do you think you took for inhalation and exhalation? 10 seconds maybe each, 15 seconds each. Now, can you inhale and exhale simultaneously? No, right? Well, that's an impossible sounding problem statement. For the last 2 years in the artificial intelligence area, machine learning, AI, or image processing, the solutions being proposed are able to solve problems which were otherwise sounding to be impossible to solve. By the way, you can do a simultaneous inhalation and exhalation. It's called circular breathing. The aborigines of Australia and New Zealand, they practice this breathing through inhaling through the nose and exhaling through the mouth. And there's a famous saxophone player by name Kenny G. He actually can play a saxophone without pausing for breathing for 45 minutes because he practices the circular breathing. Anyway, I just wanted to share that information so that it won't be too much of a tech. I'm going to talk about how to develop some deep networks for mobile devices. And when I say mobile devices, I'm talking about not just the cell phones, but also your surveillance cameras or drones and any of those things where you don't have too much of a compute power, you don't have too much of storage capacity or too much of even battery too. I'll be actually sharing a few papers published. Obviously, 20 minutes I think will not be enough to explain all the details. I'll explain the fundamental differences of how a year and a half ago image processing solutions that were proposed compared to the modern image processing solutions which are targeted for mobile devices. Have you guys heard of things like CNN and basic RNN and image processing architectures and stuff? Yeah? Yes? I remember another story. I used to teach in a university a long time ago as an interest. When I was going to my first class, I was a little nervous, and I asked a professor, how do I make sure people are listening to me or understanding me? He says the best way is if you ask a question, people nod their head vigorously or say yes, that means they're able to participate in the conversation and they understand what you're saying. So let me ask the question again. Have you guys heard of CNN and image processing architectures? Okay, fantastic. 2012 was the first year when CNN-based image processing models were released, that's when there was a dramatic improvement in the quality or the accuracy of the model. It is famously called as AlexNet, proposed by a gentleman by the name Alex. That model, that architecture had 8 layers, and it was, I think, 16.4 error rate, top 1 error rate, top 5 error rate. Then in 2013, there's almost a similar model that was proposed. And 2014, there were 2 different models. The VGGNet and GoogleNet were 2 different models. Both proposed a solution that will process images where the error rate is so low. But the model started becoming complicated. Complicated in the sense, both in terms of the number of layers and the computational expenses. And of course, ResNet came in 2015 with 152 layers. I don't know if you've read the paper. They also experimented with 1,000 layers. But apparently, the 1,000-layer model was not giving the same accuracy as 152-layer model. So they published ResNet in 2015. In all of these models, the predominant approach was take a CNN and have bunch of convolutional layers in the architecture where you have the image input into the model, a bunch of convolution layers, pooling layers, sometimes batch normalization layers coming in, and of course, towards the end, you have the fully connected layers. That's a typical architecture of all of these image processing solutions proposed in the last 4 or 5 years. If you look at the CNN, the convolutional model, you have the image, and each image has, let's say, 3 filters or 3 channels, at least at the starting layer, but once you go through the process, the input channels could be many. It could be M. You have a filter or a kernel that goes on top of the image, and this filter does 2 things. It takes the values of the pixel for that specific filter, does multiplication adds, multi-adds we call it. It does lots of multiplication, add up all the numbers for each filter, but simultaneously it looks at all the filters together. If I take the example of ResNet, they had a bunch of 3 by 3 convolutions and 1 by 1 convolutions. 1 by 1 convolution is also called as pointwise convolution because it's taking each cell as an area of focus and goes deep into the model, into the image. The convolutions, the 3 by 3s or 1 by 1s, were extremely expensive, but running on GPUs or CPUs, I think it was okay. People were able to do it, even multiple layers. But when it comes to mobile devices, devices which don't have the same compute power, they have to have a different method of doing it. Before I start talking about some of the solutions proposed in the last 6 to 8 months, this is a comparative analysis of various architectures proposed. GoogleNet, ResNet 18, VGG 16, VGG 19, ResNet 34, the inception models V1, V2, V3, V4, all of these architectures were very complicated architecture which includes a bunch of CNNs and a bunch of max pooling or pooling layers. If you look at the image on this side, the number of parameters, there are 155 million GOPS, billion ops, flops, you got to do to compute that particular architecture. For a regular mobile device, like even a cell phone, even though some of the latest cell phones, I think iPhone 10, I was told, has more than 1 billion flops, but some of the drones or surveillance cameras, etc., may not have that computing power. The earliest proposal made was in 2014 by Facebook to do a processing of face, in other words, face detection for mobile devices. This architecture was almost similar to the existing architecture, and hence it was still computationally expensive, but they brought down the accuracy to 97th percent, top one accuracy on a data set called LFW, labeled faces in the wild data set. But this model was less complicated than the previous models proposed in terms of there were only 2 convolutional layers, 1 max pooling layer, and couple of locally connected layers, the L4, L5, and L6. F7, F8 were the fully connected layers. They brought down the number of operations in the model, but still they were running to, I think, more than 1 billion operations. But still, this was really accurate. Then came the model by Google in 2015. The accuracy rate was slightly higher. But here is the interesting part. They picked 2 existing architectures. One is Zeller and Fergus, which is the 2013 model. The 2013 was very similar to the 2012 AlexNet. It's called ZFNet in 2013. ZF stand for Zeller and Fergus. They picked those 2 architectures and tried to bring down the number of operations in it. If you look into the number of flops still remains 1.6 billion. It's actually too high for a mobile device. But the number of parameters, if you look into for the Google-led inception model, it's 7.5 million only, whereas in Zeller and Fergus model, it was 140 million parameters. So you actually have 140 numbers being processed inside, which was actually too complicated. But 2014 face detection solution by Facebook, 2015 face detection solution by Google tremendously increased. Earlier, there used to be multi-billion flops, but these 2 models brought down the number of flops to less than 2 billion flops. Here, the distinct difference proposed by Google compared to Facebook was they had you see this loss function here. The objective is to minimize the loss function. In these models, they have triplets of images. One is called anchor image. One is a positive image, which is similar to the anchor, and you have a negative image, which is not similar to the anchor image. And the model is trained on, given the anchor, identify the positive image and bring the distance closer and identify the negative image and make sure the distance is longer. So they converted after the fully connected layer, if you go to L2 normalization, this layer, by the time you come to L2 layers, they create an embedding of the image into 128 dimensions embedding and do the L2 measurement, so the distance measurements. So the loss function here, if you see here xi of anchor minus xi the positive image and the square of it, they want this portion to be very, very small because the distance has to be very close to anchor, between anchor and the positive, and they want this portion of the equation to be very, very high. So the distance between the anchor image and the negative image should be very high, and eventually the loss function will be minimized in this process. So the distinct differences of this model compared to the previous model of Facebook was there was embeddings created out of images, and the loss function was very different because they were picking triplets of images. 2017 came out, Apple came out with a new model. There are not too many details available. I myself don't know what's happening there. If you read the blog mentioned there at the bottom, and if you try to read other publications about explaining how Apple is doing, there's not much of information, but Apple claims that they have used face detection methods on their phones too, and it also is of high accuracy. But I don't know too much about that. The two most important models I want to talk about is mobile nets, and then after this I'll talk about shuffle nets. Typically, your mobile devices can manage anywhere between tens to 150 megaflops of operation. A model that takes more than 150 to 200 mflops of operations, it's going to be too much of a burden on the device. So this is one model which has started doing it. If you look into the number of parameters for a regular convolutional mobile net is around 29 million, whereas mobile net as proposed in this model was only 4.2. How did they arrive at this? You guys, I think, want to go back and study about this. They introduced a new concept called depth-wise separable convolutions. So if you go back to when I started my presentation, I explained how regular convolutions happen. You have an image, you have a kernel that convolves on the image and does its mathematical operations. Normally, it does the mathematical operations of all the cells on the image and also does a depth-wise computations. People came out with a hypothesis that the depth-wise separable, that is, if you have an image with multiple channels, let's say 5 channels, 10 channels, 100 channels, the convolution which you do per filter or per channel is very independent from the convolution you do on the other filter. So depth-wise separable convolutions versus regular convolutions, if you look into mathematical equation here, let's say the size of your image is df by df, and the size of your kernel is dk by dk. Okay? Now, if you have the input channels are m and you are expecting the output channels to be n, in other words, the number of kernels you are going to use is n. The number of mathematical operations you will be doing will be what you see here at the denominator, dk by dk times m times n times df times df. That is the number of operations you would do. But when they change the hypothesis of depth-wise separable convolutions, they take each filter, do a convolution, but you don't do a depth-wise, you don't do a point-wise convolutions immediately. You take all the filters. So if you just do only per filter computations, if the size of the frame is df by df and if the size of the kernel is dk by dk and the input channels are m, for each channel the number of computations will be dk by dk times m times df and times df. That's the number of mathematical operations you have on per filter, and if you do a point-wise convolution on the input channels, it will be m times n times df by df, because the point-wise convolutions is 1 by 1. So even though you see m times n times df times 1 by 1 is eliminated. So there's a dramatic drop in the number of operations you can using this approach. The new hypothesis, like in this case, the depth-wise separable operations, this new hypothesis actually proved out to be true when you look into the results they got. So let me explain this approach again. You have the standard convolution you have by dk, and the size of the input channels is m, and when you do a kernel, so the frame is df by df, and if you have a kernel size of dk by dk, a standard convolution will have dk by dk times m times n times df by times df. Whereas if you do a depth-wise convolutional filters, you take dk by dk times 1 because you're taking 1 for each filter, and then you add the point-wise convolutions, in this case 1 by 1 size kernel, through the entire input channel of M. This dropped the number of operations dramatically. This is the architecture the authors propose. If you look into, you have the regular convolution, then you have the depth-wise convolution, you have another regular convolution, you have a depth-wise convolutions. They follow this approach, and then you have the fully connected layer, and then when you do a classification using softmax, the accuracy actually jumped for these organizations. And also, if you look into the standard convolutions, people were normally using was 3 by 3 convolutions and batch normalization and ReLU. In this case, they use a depth-wise convolution, batch normalization, ReLU, and then 1 by 1 convolution. So, because they were disconnecting the depth-wise and the point-wise convolution, the number of operations dramatically dropped, and accuracy remained the same. So, let's talk about ShuffleNet. ShuffleNet, I think, is published in 2017 by a private organization, Face++, I think is the name of the company. They took the logic one step further. You do a depth-wise convolution on each filter, but you are still doing a 1 by 1 convolutions or a point-wise convolutions, and many times the 1 by 1 or the point-wise convolutions actually itself constitutes 95% of the mathematical operations. So, this paper for the first time suggests, why don't you do a depth-wise convolutions, they call it as group convolutions, not just per filter, but also for when you're doing 1 by 1, there also do the same depth-wise convolutions. So, in this image, you have three different channels, and you have a regular group convolution you're doing per channel, and then you extract the features out of it, and then run the second group convolution on that, and you get an output. But this is what the previous paper suggested, but in the new paper they said, because we are not adding up the information from each filter, the model is trying to learn a lot more from the same filter, which is not a comprehensive way of learning. So, they want at certain layers the model to look at all the channels of the incoming image. So, they suggested to actually have information being procured from each of the filter, and instead of doing mathematical operations on all of these, they just shuffle the input filters and then do the mathematical operations on top. In summary, the mobile nets used the 3 by 3 and 1 by 1 convolutions from the previous architectures, where the 3 by 3 was converted using a depth-wise convolutions, but they retained 1 by 1 point-wise convolutions. But in ShuffleNet, they did not just for the 3 by 3, but for 1 by 1 also, they did a depth-wise convolution, and they actually got a good results. This is the architecture, and the number of, if you see the number of parameters is only 140 million, not too many. Google published recently a paper, and it's already in production too. When you take a picture using an Android device, it immediately adjusts two distinct features in the image. One is the colors or the brightness of the colors, and second is the sharpness of the edges. So, they've trained a model which will identify or focus on what colors are not up to the standard and how to adjust those, and which of those edges are not up to the standard and how to sharpen that. This actually, it's a complex paper. If you guys want to read this, I think it will be nice. But the benefit of this is it runs, I think, in 20-25 milliseconds, so it's actually almost real time. The moment you click, you will see the model updating, and changing the picture. The most exciting thing I'm interested about is Capsule Networks, and if you have not heard of it, I think you should go read it. Jeff Hinton has been talking about Capsule Networks for the last couple of decades, and I think as recently as 2011, he talked about how CNNs are really the worst type of models that can process images, but the bad thing is they work so well, no one wants to actually experiment on a different approach. And he has been talking about Capsule Networks, and he published a paper in October 2017. The Capsule Network has an important distinction, and that is here. You see the image here. This is image of a face with eyes and a mouth and a nose. This is some random picture which has a mouth here, a nose here, an eye here, and an eye here. A CNN-based architecture will not see a difference between the two. It just looks for various features available in the image and then makes a classification. Whereas in Capsule Networks, it actually looks at not just the various constituents of the picture, but also it's called pose. In other words, the hierarchy of the image. For example, you not only have to have a nose and a mouth and two eyes, but the eyes have to be on the upper portion of the face, and the mouth has to be at the lower portion of the face. That distinction in terms of the hierarchy of the image is also captured in Capsule Nets. I personally believe Capsule Nets may make a dramatic impact on image processing going forward, and they may also actually have a dramatic impact on mobile devices too, and how to process images in mobile devices. That's my. How much time I have? We're done? Oh, no questions? You know, there are two reasons why there are no questions. One reason is I was so brilliant. Oh, you have a question. And second reason is nothing. Yes, sir, go ahead. Thank you. Oh. The question is, other than the image processing and video processing, where else deep learning has impacted? I don't know. It has impacted almost every walk of life, whether it's a healthcare or transportation, manufacturing, high tech. You can have lots of regular machine learning, statistical machine learning solutions being applied, and you also have lots of deep learning solutions being applied. For example, healthcare is one huge area where there's so much of investments happening, where people are using NLP and using deep learning models to actually process text, to extract information from unstructured reports. That's one massive area. And any healthcare, whether it's just the regular healthcare or cancer or DNA processing, could be anything. And of course, any online company or manufacturing company where there's lots and lots of text available, they're using deep learning. So I think that's I don't have time to explain all the potential use cases, but deep learning is being used in almost every walk of life. People talk about being hyped, but I personally don't believe it's a hype. Thank you. You had a question? I can't hear you. Have I implemented? I've implemented a couple, not the Capsule Network. I have not implemented that, no. Capsule, I don't think the code has just been released recently. There were only two papers published by these gentlemen. One is still under public review, not really accepted for publication yet. One paper is already published. It's already out in the market. And they have evidence now that their Capsule Networks are doing some positive results. They have done it on MNIST dataset, and they have found some decent proof. But you can find that online. Yeah, the Capsule Networks are not done yet. They're not completely developed yet. Thank you, guys. Thank you. Yeah.